Hello. What we're going to talk about this time is about how we can use sets to define number systems. Well, first of all, the system of natural numbers. Now, one can argue forever exactly what is the number 2, for example. But what set theorists do is just say, we're going to take some representative sets and we'll just assign these sets to be the natural numbers. Right? So this was first thought through by Zermelo, and he made the suggestion. He said, well, let the empty set represent 0 here, and I can have 1 be the set that represents the set of the empty set, and then 2, he just stacked up extra brackets around them. So 2 is the set containing 1. This is the set containing 0. And in general, n plus 1, I won't draw all the brackets, is the singleton set containing n. So this is fair enough. This will do. This is just saying, okay, I'm just going to name this set here as number 2, and I'll use that when I start to construct ideas about addition and multiplication and so on. But actually, the one that's come down to us is actually a more useful suggestion, which was of von Neumann. So this is Zermelo's numbers. And it wasn't until 30s till great mathematician von Neumann made a different and actually superior suggestion. He started off with 0 being the empty set again. So this is the von Neumann. This is a Hungarian mathematician, the von Neumann natural numbers. He made the suggestion that we should have 1 again, the set that contains 0. Right. But 2 should be a set of its predecessors. And 3 should be then 0, 1, 2. So of course this will now have, well, 3 elements. And in general, n plus 1 should contain n elements. So each number is the set of its predecessors, and it has the added advantage that n plus 1 has got n plus 1 elements. And moreover, these are all transitive. We shall see these are transitive. So this is a more useful suggestion, or nicer suggestion. And this is the one that set theorists use rather than Zermelo's suggestion here. Okay, so we're going to take the von Neumann natural numbers here, and we're going to work our way towards eventually defining addition and multiplication on the natural numbers. But first of all, we want to talk a bit about induction. We want to be able to, in the end, talk about defining addition and multiplication using recursion. And to get recursion going, we need not just the natural numbers, but we need the set of natural numbers. So we want to see how we can define the set of natural numbers. Well, you could say, well, haven't you done it here, right? But I want a set that's going to represent the natural numbers, all of them, right? Each natural is represented in terms of its predecessors. And what we shall see is we shall define something which we shall call omega, and this will be the set of all of the naturals. Like this. So this will mirror what we've done before. A number is the set of its predecessors. So this new gadget will be the set of its predecessors. But actually this is not how we proceed, right? We will have this result, but we're going to define first of all, following Daisyin, what are the collection of inductive sets. So this was an approach by, as I said, Richard Dedekind, and we're at definition 2.1 now in the notes. So a set is called inductive first of all, the empty set is in there. And for anything that's in there, its successor is in there. So for any x that's in y, the successor of x is in y. So recall what we had last time. The successor of x is x union singleton x. So these are kind of closure conditions. 0 is in there, and for any x that's in there, the successor of x is in there. Note that the successor of n, as we defined it on the previous board, this is supposed to be n union singleton n. And this was just what we called n plus 1. N plus 1, all the elements up to n, and then n as well. So a set is going to be inductive if it contains 0, and if it contains n, it contains n plus 1. But actually, it doesn't rule out there being other things inside there, inside W. Inside y. Here might be y, our inductive set, and we're told that it's got the empty set in it, and also it's got the successor of the empty set, and it's got the successor of that. So it's got this chain of things closed under the successor operation. But what it doesn't rule out are other things inside y. Maybe there's some other set u in here. Right. Well, closure condition says, okay, s of u is also in here. And so is s of u. And s of u. And so on. So being inductive says that we've got at least this chain in there, but maybe there are other chains with other starting points, many of them, in fact. So an inductive set is too large a set for consideration as the set of natural numbers.